I plan on pulling a thread basically all the way from the interpreter all the way through the code and back basically. So it's a lot easier to sort of understand when you do it that way.
Mm-hmm.
But we'll see.
Yeah, I'm looking forward to it. It should be good.
We do have this mindset problem between sort of traditional HPC developers and what we're striving for with Arkouda, because we're really striving to get, we had an instance where an analyst came up with a behavior they were looking for on a Friday. On Monday, we took a half an hour. We talked about the statistics of how we might detect that. And then in 15 minutes, we wrote the code, right? I mean, it's really that the whole purpose is to really shorten that amount of time to get to the first solution, right? So that you can iterate on it, because people change every day. The tradecraft people use changes every day, and it's not like a physics problem where you're trying to solve Schrodinger's equation or something, and that's true for many decades, right? where the things we're trying to solve a lot of times they come up, it's a change in behavior from one week to the next, and we have to write new code to actually address it, right? And we don't have a lot of time to optimize things typically. So I hope this is going to be very interactive today. I am going to bring up the GitHub. We're going to walk through a couple of slides because architecture diagram was asked for yesterday, and we're going to talk a little bit about IO configurations that we've been able to run with, like file systems. One question was, does the file system have to exist in the client and the server? And the answer to that is no. We've been able to exist in places where the client and the server were not on the same box or in the same, even on the same network. In those cases, we've had to use things like, SSH tunnels and relays and things to get it to work, but people have been able to do it, right? So anywhere you can get a 0MQ socket, you can basically connect the client to the server. We even have a person who's running Arkouda now under the Windows subsystem for Linux, so it even builds there. I have not done that myself. I run on a Mac all the time, or on a Linux InfiniBand cluster. There was a couple of different requests from yesterday, so we might show like one slide about InfiniBand performance of the sort. I'm going to pull a thread through two parts of the code. I'm going to pull a thread through basically just some simple arithmetic operations, and then I'm going to pull a thread through the sort and show some of the sort of how we layer the code, basically. I'm Mike Merrill. Hopefully everybody sees my name. And I'm the originator of Arkouda. I told people what I wanted a dozen times before I sat down basically with Brad and talked about implementing something. And that was Christmas of 2018, right? So in a fever, I implemented the first version of Arkouda in about a month and a half. Gave a demo, and then people go, oh, we know what you want now, right? So sometimes you have to show people things to actually get them to buy in and get on board, right? So let me share my screen. Make sure that I'm, just to show you, I started up an Arkouda server on my Mac. Over the lockdown, I upgraded my Mac to 128 gigs of memory, so I could run pretty much almost anything I want now. Anyway, so this is, let me get back to the screen sharing. I'm gonna stop that one and I'll start a different one. Let me get, does it share? I want to share a Safari. The thumbnails are too small. Let's try that. Oh no, that's not the right one. Okay. Stop share. I got too many windows open. Okay, there we go. Okay. Nope, that's not the right one either. Crap. Which one is the one I want? I want this one. Too many windows open. I'll just share my desktop. Can you guys see my desktop? And then we'll go with this one, and I'll just cover everything. Okay. So everything I'm going to talk about assumes that you guys know, like, you can get to the Arkouda repo during me talking, because that's where we're going to go over the code, and everything is linked off of the Arkouda repo on GitHub. So we'll scroll down to the README. I'm responsible for the artwork. So, you know, if you have any gripes about it, it was free. I drew it. So let me, this also, we're also going to be maybe going through the Arkouda online documentation a little bit. The best place right now to do that is on the Arkouda docs at GitHub pages, which is linked out of the README at the top of the README. The other one links to read the docs, which we're going to probably stop using. The reason why is the one on GitHub actually includes all of our Chapel documentation, which is still in the works, that uses Chapel doc to generate. Read the docs didn't have a good build flow, and so we started using the CI on GitHub to generate the documentation. Anyway, I am gonna swap over real quick to one of my. So this is what the front page of the. Can you guys see it says "Welcome to Arkouda documentation"? Is that good? Okay. Yeah. This is what the front page of the Arkouda documentation looks like. There's some pages we've written to try to explain sort of how things go together. Down at the bottom, there's API reference. That's the Python API. It's generated by the Auto API package. And then the Chapel API reference is generated by Chapel doc from the code. Don't yell at me if all the comments aren't exactly right. There's a lot of documentation to keep up with, and there's a little bit of technical debt in the documentation right now. But at least you can cruise, like in the Chapel doc, which is probably where we're going to spend most of our time. You can get down to the Arkouda server, and then that sort of gives you a top level of the Arkouda server, like what procedures are in there, and what the, you know, how you use it. But you can't actually import it. It's the file with the main procedure in it. So anyway, let me go back out of here real quick, and I'm gonna, oh, there we go. Let me see where we are. Okay, so someone had asked yesterday about I'm going to do a really quick run through of Bill's talk from CHU last year, because there's a couple of slides I want to focus on. Let me just flip through here. This is linked out of the README if you want to bring up the slides yourself. But so this slide represents sort of the high level architecture of Arkouda. you run a Python client. Usually we use it usually linked into a Jupyter notebook, but that doesn't matter because the Python can be a Python script, or it can be a Jupyter notebook, and that connects through the client, the Python client that we've written, through a 0MQ socket to the dispatcher in the server that's written in Chapel. The server is sort of a well, I'll let you see it. It has a main dispatch loop. And we wrestled back and forth with whether we were going to implement this as a function table or whether we were going to implement it as just a big select statement. And we ended up with the select. It was basically the same number of lines of code. It's much easier for a beginner to deal with the select than it is for them to deal with a table of function pointers. Anyway, and then we have code modules. The code modules are effectively divided in half. Each module, some of the modules are factored this way. They have a message processing function, which basically processes the message that came in that actuates the function. And then it calls an array level where it takes a raw Chapel array, right? So the procedures are developed or divided into two levels. And then usually in message processing, we do lookups into the object store. It's basically called the symbol table in the server. And that holds objects on locale 0 that point at distributed arrays that are distributed across the system. Now, there was a question about, I want to make sure I cover this. There was a question about I/O and file systems. It is not absolutely necessary that the same file system is visible in the client and the server. If you're going to, but obviously, if you want to read data from the server, it has to have access to the data, the directory where the data is, right? So there's two methods we went over yesterday about how to get data into the server. One is read it into the client and then do a binary serialization across the 0MQ socket and create an array in the server, or read it from a HDF5 file in the server. So hopefully that covers, like, at a high level, sort of the architecture. And then when we walk through the code, you'll get a deeper understanding. Hopefully it's not that difficult. Okay, so let's see, what do we got here? I need this. That's the server. That's the client. Okay, so what I'm going to do is I'm actually going to start from a simple notebook that I wrote and put in the Arkouda notebooks repo. And I'm going to actuate, I'm going to connect to a running server, and then we're going to look at some of the messages. And then we'll dive into the code and we'll look at the code path. Okay, so we did this yesterday, but we basically import Arkouda. Then this notebook's basically implementing Euclidean distance and cosine distance between vectors. I define a few functions. It's a pretty simple notebook though. So I import NumPy and SciPy, and then I do a connect. Is that getting too low on the screen? Is that visible? Okay. Then I call, okay, so now I've connected, right? So let me go back to the share and we will connect. Oh, I could have just done that, couldn't I? Just did that. So now I am running a server, and you'll see that when you connect, the server transfers. You'll see this is an example of one of the traces that we save for every run. In production, we save these to files, but anyway, it basically, these.
I'm seeing your browser window in front.
Oh, you're seeing the browser window. Okay, so let me do this. Let me go back. Let me say desktop 2. There's desktop 1. Okay. Let me do this. Is that better?
Better.
Okay. I shared the wrong desktop. I got 2 monitors and I just shared the wrong desktop. Sorry. Okay. So there is a in the trace, if you see 3 arrows this way, I'll highlight them here. That's a command that's coming in. And then everything to the part where you see 3 arrows going back the other way, that usually says how long the command took to return a message. And then typically there's a reply message that is also printed. That's somewhat of a debugging thing that's left over. Anyway, so the connect works. It passes back a connect. You'll see that it says that the message type is normal. There's a high-level message that's wrapped in JSON that's basically holds the command and the data, and whether that data is binary or a string, basically, when the message comes in. Anyway, then once it does the connect, it calls get config, uses the get config message in it, basically lets the client know what the configuration is. We stuff stuff in there like what the version is, what 0MQ version it is, what HDF5 version it is, just so that we can see what we're running against. Okay, let me go back to, oh crud, this is going to make everybody dizzy. Where is, did I literally just get rid of that window? Did I kill my, where is it? Stop share. Did I kill the window?
Is it in your second screen?
Yeah, I'm just like, I'm a mess here. That's fine. Let's see. I'm just gonna grab a I'm gonna grab another copy of the. Wait a second. What happened? I'm gonna grab. And then I'm going to pull this over here. And then we're going to share this. And we'll go like this. Oh, that's not what I wanted. Oh, well, whatever. All right. So let's do this. Let me grab, I have no idea where that went to. That sucks. Okay. So let me, anybody wants to know where the Arkouda notebooks are, they're linked off of my, that's where that's linked to. Let's see. This is really annoying. Now I've screwed up everything. Okay. Okay, here we go. Oh, when I went full screen, it made a third screen. Ah, that's where it all went. Okay. Okay, so now we're going to make a call to Arkouda in this next cell. And it creates 2 vectors, A and B, that calls randint. Maybe we'll just pull the thread through randint. That'll be easy. And then they're numbers 0 to 10. and it's 100 long. The array is 100 long. So now let's go back here, and you can see a bunch of messages appeared in the server. And you'll see the randant here. This is the message coming in. For some reason, it's not printing. Huh, weird. It's not printing the arguments. I wonder if something happened. Okay. Probably a commit that went awry. Anyway, so let's go back to let's go back here. This is in the repo in the Arkouda subdirectory where the client is and all the Python code. There's a file called PD-array creation. So we had to call it something. So we basically started calling them PD arrays for parallel distributed arrays instead of ND arrays, which is what NumPy uses. So let's do this control. Let's see. Okay. Let's see. Okay, here we go. So here's the beginning of this entry point. We call randant. It takes low, high, size. And then and we use a package called TypeGuard to allow us to limit the types. It does runtime type checking in Python. So that's what these numeric scalars is actually a group of types that we allow, right? And PD array is the type of the object. Anyway, this is the doc string. There's more doc string, and then there is actually, and here's the code, starts on 598. We normalize the type. So we do some magic with Python to make sure that at runtime, we can take a bunch of different types. So we normalize the type. And then down here, you'll see this message on message. There's a generic message function on 608. Is everybody following me? The command is randant. The args are put into a string that's formatted basically with a Python format statement. It's the size, the name that we want to that we're giving the type. That's the name of the D type, which comes from NumPy. Low string, high string, and C. These allow us to obviously call. It's a remote procedure call effectively to the server. And then the return is a rep message. And we have a function called create PD array, which creates a Python object with the right handle in it and all the right attributes. It's a factory basically that mirrors the handle and all the attributes on the Python side that points back into the server. Okay, so that's the entry point. Now what happens? This message flies across that 0MQ link. And here's the main. We're in the Arkouda server.chapel in the source directory. So if you go into the repo in the source directory, that's where the server source is. We include a bunch of stuff, and then down here, we do some things like check to see if it's a binary message or a string message. We do some other stuff like that. Anyway, we wind down through some of this code, and then we end up at this select statement, right, on 301. And these are all the major commands that the server accepts currently, right? So it's sort of like a major and minor opcode in some cases. Array is a binary serialized array from NumPy to the server. So if we want to push a NumPy array into the server for some reason, the 2ND array, this command basically pushes it back to the client, right? So array pushes it to the server and 2ND array pushes it back to the client. But let's scroll down through here and we'll find they're not in any particular order. Random, normal, here's random right here on line 345. Now, all these functions have the same type signature. So they could go into like a function lookup table if you wanted. They all take, they all look like this. Like this one's called randint MSG. This is the message processing layer of the server. So we go through the main dispatch loop. We end up here. It has the command, the args, and it passes in the symbol table so it can operate on the symbol table. So then I'm gonna go back to the source directory, and then there's a function called randmessage.chapel. And this contains all of the random number generators that we have. This might have been not a great example because this particular message, do we call? Oh, okay, so we do. This is a good example, actually. So we, on line 31, we have this randint message. It takes a string, it takes a payload, which is the rest of the arguments for the command. And then it has a symbol table and it throws back, it basically sends back the reply tuple that we're gonna reply with. But as we're going through here, we have to create, like here, we create the name of the thing that's going to get put in the symbol table, like the result name. That's what our name stands for. Up here on line 35, we're actually splitting the message based on spaces. Some messages are split based on spaces. It's just strings that are flying back and forth right now. We've thought about using JSON, but it incurs a certain amount of overhead. So we haven't done it yet. So this thing gets split into 5 fields. It's the length string, the D type string, the minimum, the maximum, and the seed for the random number generator. So then there's a select. The first level select in a lot of these message processing functions is on D type. Since Python is a dynamically typed language and Chapel is a statically typed language, right? We have to basically know what type. Once we get into Chapel, we have to know what type we're going to operate on, whether it's an integer or a float, or like here's this first when clause right here on line 47 is for D type is int 64, right? And one of the first things we do is we check to see if the creation of this array is going to be over the memory limit. And we track memory currently. You can turn memory checking on or off. We typically run with it on because every once in a while the user will sit at the prompt and they'll say something like, I meant to type 100 billion, but I added a 0. And the next thing I know, I'm going to allocate a trillion element array, and I might not have enough memory left for that. So we have to be able to catch that. Otherwise, the server will crash because it will go off and try to allocate something that's not possible. So this over mem limit thing is littered around the code to basically make sure that we don't crash the server if someone tries to allocate too much memory. And then we take those strings, we turn them into integers, That's what the min and max these things are doing. Then I don't know how many, hopefully everybody's seen Chapel code before, but and we call the logger. If we're in debug mode, it'll put out a message. And then we call fill int, which is like the array level, what I was talking about before. I mentioned it. This is a function that takes sort of bare Chapel arrays and not like a string message that actuates the function, right? So, so that's sort of how that works. Then we would call the fill int method here on line 57, and it would fill the array with integers between min and max and with the seed, right? Using the seed for the random number generator. Does anybody have any questions at this point? Is that pretty clear, or did I go too fast? Or I guess I'm doing okay. Unless somebody says stop, I'm gonna keep going.
I have a question. So is it possible to so here you creating essentially a Chapel array with random ints, but is it possible to tell the server to populate an existing, I don't know how much sense would that make, but an existing array with random ints, the one that's been previously created, or is it always generating a brand new one?
So, right, we're in Python. There was only 2 of us that wrote this code to begin with, and we had to make some decisions about whether we were going to modify arrays in place, because all we have on the Python side is a handle. And we chose sort of more of a single assignment paradigm. So we're constantly making things and destroying them. And it's mostly because when you string together operations, you have an operation that takes in something and then it leaves something in the symbol table for subsequent operations, right? And if you start modifying things in place, you can run into some really weird behavior that you as a user can explain, right? And actually, a lot of our users are mathematicians, so they really, they understand like how code works and they can write Python code, but they don't understand how reference counting and object creation and a bunch of other stuff works under the covers. And so we rely on, you can assign the same array to multiple Python objects. And you can, because it's all by reference, right? And you can do other things, but there's only one operator currently in Arkouda that doesn't create new arrays. And that's like plus equals. Right. It modifies, and that's the only one that modifies arrays in place.
Okay. I understand the motivation. You don't want people to be shooting themselves in the foot. I was thinking more from a viewpoint of somebody that, writing a compiler for the front side and knows what they're doing and wants to reuse.
Yeah. It could be done. It could be done. It's not it's a paradigm we've chosen to follow in all the things we've implemented. It doesn't mean you couldn't take a version of the Arkouda server and make it do what you want to do.
So a short answer is every message when you're computing something creates a new array on the Chapel side, right?
Currently, yes.
Okay.
Currently. And it really is to keep it's to make things debuggable and to make sure that users don't shoot themselves, basically.
Sure. Thank you.
Okay. So then we get, after we fill this thing with integers, it drops out of this select and it creates what's called a reply message on line 108. And the reply, or the response, it's a response message. Anyway, sorry. It's request response anyway, but we call it REP. And then what we send back, if we create one array, we send back the word created, and then the attributes of that array. And that is from the st.attrib. You pass it the handle, which is the string name of the array, and then it stringifies the response, the attributes basically. And so we add those two together. If multiple arrays are passed back, the word created is prepended with the plus sign. And the first array will say created, the second array will say plus created. And that way we know how to parse it all. And we have a lot of things that pass back multiple arrays, multiple array handles. And then down here on 113 is the message that does the normally distributed generation. Yeah, I think this one really only takes floats. Anyway, okay. So let's go back. Let's go back to the Python side in the notebook, and you guys are seeing the notebook, right? That's good, I hope. So I define a little function here that basically checks to make sure things are PD arrays, because I don't want to add a PD array and an ND array. Originally, we had an iterator that would just pull data from the server back to the client just automatically. And that became a real problem because we had users trying to pull back a terabyte of data. So right now, there is no iterator for a PD array. And it's really to keep people from, you can iterate over the elements of a PD array one at a time if you want to, but you can't, if you try to transfer a whole PD array or something, it will, if it's over a gigabyte of data, it'll spit out a message that says something like, you tried to do this. Is this really what you wanted to do? If you want to do this, then you need to reset this variable in the environment to be bigger so that you can transfer more data, right? It's just a friendly way of warning the user that they're trying to squirt a terabyte of data across a 10 gigabit link or something. It is interesting as you're in development of one of these things where what things were never issues when you're writing statically compiled programs, and then what things become issues once an interpreter is connected to the other end of your and to your keyboard. You can just type whatever, and you have to be able to catch things, right? Okay. So I just defined this function called check PD array. Then I define the next thing I'm going to define is a dot product function. So this is going to call a few things. I don't know if anybody's familiar with it, but you can actually, if you really want to, you can get the source to a function in Python, and you can actually compile that to an AST and then walk the AST. And we've talked about doing that, and maybe squirting like some ASTs or things like that across the wire to the server, but we haven't gotten that sophisticated yet. I don't know if we will ever get that sophisticated actually, because this is working pretty well for us. So I defined this function called AK dot. We check to see if U and V are PD arrays. If they are, then we don't throw any exceptions, and we go down and we do the sum of the multiplication, which is basically the dot product. And once I execute, this is just a definition, so it's not going to. And then there's a magnitude. And we could implement these as server messages, and we've talked about that. Usually what happens is there's multiple tiers of implementation that we could engage in. since we have so many server operations right now that we don't have to, we can typically compose the thing we want, and then we look and see whether we think it's fast enough. If it is, or if it's not fast enough and people really want it to be faster, then sometimes we'll combine some things together and make a new server operation. So you can sort of think of this set of messages as an instruction set, and we can extend the instruction set. Okay, so that was Euclidean distance. I had a user ask me for a Euclidean distance and cosine distance, and so I implemented both of those as functions in Python and passed him this notebook back. So this cell basically just checks to see whether the output matches the SciPy routine for cosine distance. And then this one basically just matches the same thing for Euclidean distance. And then this is next one is a disconnect. So we can connect and disconnect scripts and notebooks from the same server. And we actually have a set of registration methods that allow us to say, when you exit, don't delete this array, right? Save it for the next thing that runs, right? It's sort of like, in MATLAB, you can sort of get a top level of like the top level variables, and then you can say, well, clear this variable or clear that variable. That's sort of what we've implemented. It's a little bit kludgy, but it allows us to string multiple tasks together in a pipeline where they don't all have to be in the same Python script. Okay. Is there any questions at this point? Let me go back to, let me go back here. So like now you'll see in the trace, there's here there's binop VV in the middle of the screen. So what binop VV stands for is a binary operation between a vector and another vector, right? Whenever we hit a new memory high watermark, we print out a message. That's what that comes out of that check memory limit function. It either prints out a message with a new high watermark, or it throws an error if you try to allocate more memory than you have. And we go off of physical memory because it is incredibly difficult to calculate, maybe even impossible to calculate how much virtual memory there is attached to a OS instance. And we don't want to be swapping all day. Most of the systems we run on, if we get outside physical memory, we've done something pretty wrong, and our performance tanks at that point anyway. So here's a response to this binop VV. Wow. This thing is okay. Anyway, so this created a they took the whole message out. Wow. I'm going to have to put in a PR to fix that. Okay, so created ID 8. This is a server assigned name. There's a 64-bit counter. It creates a string. It's called ID underscore and then some number. And then this is just one up forever. So if you ever allocate more than 2 to the 64 names, things will crash. They might not though. You might just wrap around. Anyway, it was an integer 64 vector. It was 100 long. It has one dimension. This is the length of the first dimension, and this is the element size. So let's go back. So let's dive into how that works real quick. This is a much simpler message in a way, but there's a file called pdarray class. And where is, okay, here on line 70 is the class definition for a PD array. It has a bunch of operations it supports. If you know Python, then you know that you overload these functions on the class. Let me go here, like for like add on line 262, there's an add. Add calls this bin op. Other is the other object you're adding. So self plus other is basically what's going on here. And we support integers. We support an array as the first argument, obviously, an integer and a float as the second, or a PD array as the second argument. And Python has this weird thing called radd. So like this rmod and radd here on line 265. Radd is a reverse add. So if the interpreter figures out that you're adding an integer plus a PD array, it can call the PD array operation for radd, which says that the PD array is the second operand, right? Anyway, so those things call underscore binop and underscore rbinop, which are two functions that are defined above. So here's the binop function. This basically just takes an operand and a string. It figures out what the type of it is, and then it winds its way down and calls. It calls generic message, which is the with the args and the command. The command is either binop vv or binop vs. Vs is vector scalar, vv is vector vector. Anyway, so where does that come out in the code on the other side? That basically goes to the server. I'm going to scroll down here real quick. And on line 328, there's binop VV, and we call the binop VV MSG, which is in, what is it called? Operator message, I bet. Operator message. Operator message.chapel. Okay, and then binop VV is on line 38 here. And it takes this command, a string, a payload and a symbol table, just like all the other functions do. It knows that all these messages only have 3 fields. It has the op, the A name, and the B name. So operand 1, operand 2. And then it drops into a select statement that selects based on the left D type and the right D type. So it has to know if it's adding integer and integer, or integer and float. And so it has to select out the right thing. When those two things are integers, you drop into the code on line 55. The left operand basically pulls a symbol table entry out and casts it to an int. The right operand pulls a symbol table entry out, casts it to an int, basically our array of int, right? And then plus is, there's only 2 lines of code that actually get executed here for each one of these operators. So there's a lot more code that's actually involved in like selecting what you're going to do rather, other than doing the code. Excuse me. So on line 63, I sort of commented the first one. I didn't want to comment every operator because there's a boatload of operators. I forget how many lines are in this file. Probably quite a few. Some operators just work, and other operators like division have to be made to work exactly like NumPy. So division is one of those ones it's a little bit different than the other operations. You have to do more checking, and you have to actually, especially for floating point, you have to deal with nands just like NumPy deals with nands. And Chapel doesn't necessarily deal with nands in the same way. So we had to fix it up with some extra code. Anyway, so there's basically, we're line 63, we're adding an entry to the symbol table with the return name. That's what our name means. And the size, I just use the size of the left operand. And I make it an integer array entry. And then E.A is the .A is the array element of the object of the thing that's stored in the symbol table. So E is the entry that we just created on line 63, and E.A is the array that was created there. It's originally Chapel initializes things to 0, so it's initialized to 0 when we get it. Then L.A plus R.A basically is what we, and these array, this is deceptively simple because these arrays are actually, they use the block distribution from Chapel, and they're actually spread across hundreds of nodes sometimes, right? But it's actuated by this one line of code. Anyway, so then down on 73, you can see we do minus, we do times. These are all the things in this section of code are all the integer operations that work between a 64-bit integer and another 64-bit integer. So then down here, we have integer and float on line 160, and that's how that's implemented. You can actually see Python has two different division operators. It has true division, which always returns a float, and it has floor division, which returns an integer, I think. Anyway, so line 177 implements true division, and line 181 implements floor division. And that had to be implemented, like floor division had to be implemented with a array comprehension from Chapel. Okay, anybody have any questions so far? I was hoping I'd get some, like, why'd you do it this way, or why'd you do it that way? Anyway, I'm just going to scroll down to the bottom. There are operator equals. So there's bin op SV. Here's another one, right? There's VV, VS, and SV, right? Are the three different operators that we have, classes of operators we have. So each one of these cases implements a different, obviously a different type combination. Then we have op EQ VV, which is an operator equals. So that'd be like plus equals with two vectors. This is all the simplest. This was like the first code that got implemented. And it's really simple, right? I mean, compared to other things in the code. But you get the general flow, right? The general flow is we get a message. We don't remember any messages that came before. We only remember things, artifacts that are placed in the symbol table, right? That way we can string together anything. Let's see. So there's 1678 lines in this file. So there's a lot of different combinations here. Let's see. Let's dive into a more interesting thing. There's a thing called extremas.chapel. This implements min k and max k. So like it does specialized reductions. So if you want to look through this code, this was written by one of the, so this is an array level thing. This does not process, there's no message processing in this file, but this is what's necessary, I guess, to do the custom reduction operators in Chapel. I don't know, Brad, is that? This really isn't a published interface either, right?
Yeah, it's there's some things that need to be improved about it, so we've kind of avoided documenting it for that reason.
Yeah, yeah.
It can be used. It's just in using it, people should be aware that it's going to change out from under them in the future, probably.
Yeah. So let's go through one of the pieces of code that's like at the heart of a lot of what we do. I like, you have to support all these operations so that you have a complete set or a complete enough set so people can write somewhat arbitrary code. Like the operators we have to support indexing operators. So like, where's index message? Indexing message, right? Indexing message dot chapel. So this is on line 25 in this file. There's a procedure that basically takes an integer index into an array, right? And that maps back to this get item overload in Python, right? So in Python, you can pass slices and you can pass integer indexes and you can pass like array indexes all to the bracket operators. And that calls this method in Python called get item. And then there's another one called set item that allows you to do scatters, right? So if you look at the PD array class, we go back there, you can see, let me see, there's, okay, so on line 449 is the get item, and it passes self, which is the object you're operating on, and then key is what is basically a Python object that holds the, it's either an integer index or a slice or a pointer to another PD array. And so this code goes from 448 down to 476. And we allow a single integer, we allow a slice, and we allow a PD array, right? And then if it's outside of those, it says unhandled. It'll print out a message saying unhandled key type if you try to pass it something else. And then that translates back into a bunch of functions that are in this indexing message.chapel, right? So there's integer index, there's sliced, which is like, you know, you could say 1:2:-1. I don't know, right? You know, and it's start, stop, and step, right? And we have some code that basically it makes its best attempt to translate a Python slice into a Chapel slice. And then so we can directly use it. So on line 68, we have slice indexing. So this is all about, I term this whole category of stuff as like gathers because they happen. You're basically indexing something. You're not setting a value anywhere. You're just indexing something and you're passing back the things that were indexed. Like line 126, we're taking a PD array. One thing that we do support here on line 179 is Boolean indexing, which has its origins. I mean, the first place I ever saw it was in MATLAB. So if you index something by a Boolean array, you can think of that as it compresses the array based on all the true values. So you'll get an array out that's equal to the length where all the true values were in the index array, basically. and it pulls those values and compresses. So I call it compression indexing, which is what the comment says here. And this helper function is actually a helper procedure is a nested procedure. So it knows about everything in the code, but we pass it the type so that it can specialize. So it's specialized at compile time by Chapel for each type of input vector. So there's Boolean, float, and integer are the input types. That's what this X type is. Anyway, so then we make some refs for performance reasons, because sometimes, since the object that holds the reference to the array is on locale 0 in the symbol table, we have to make a reference to the array so that we don't keep going back through the root object to get at things in the object, right? Does that make sense? It's a performance enhancement, right? Then I create, okay, so truth is the Boolean vector, E is the entry in the symbol table, E.AD is actually the domain of A, E.A is the actual array, truth is the, obviously the Boolean vector. And then we have a copy, we have this funny looking thing in here. It's a copy aggregator. And at some point, is Elliot on the call? At some point, I'll let Elliot describe copy aggregation, but we have these communication aggregators that sort, they basically do local gathers and remote scatters of vectors of addresses and data, so that we can pack messages that are big enough to basically make InfiniBand work for us, right? The original code worked okay on the Cray Aries network, but when we got to InfiniBand and Ethernet, things really didn't work well. So Elliot wrote these copy aggregators, and we use them in 40 different places in the code, or 50 different places in the code. We use them all over the place. So it's gotten us, like, I don't know, more than 100 times performance on InfiniBand, because InfiniBand is so bad at single word messages. Okay, so that's a copy aggregator, and you'll see those things all over the code. So down here on 208 is actually where we select on the types, right? So we have a input type. GX is the vector. You can think of it as the X vector that I'm going to gather from, and IV is the index vector. And so then, it's an integer with an integer index vector, or it's an integer with a Boolean index vector. And then we go through all the types, type combinations here. Otherwise, we basically flag an error, and we throw an error, basically. You can throw, from a bunch of these routines, you can either throw an exception, or you can just pass back a tuple that has error type. So there's two different paths basically to get an error back. But let's see what else. This one here's the scatter, is set index to a value. So if we want to set a particular index in an array to a particular value, this is a response to the set item call of int and value, basically. So this is the index, and then this is the value you're going to set. Anyway, let's see. I could go through all these. It's not really worth going through all of them. This is code to do a PD array to scatter This is code. So this is a sub, it's got an index vector, and we're going to scatter a single value into a whole bunch of different places, right? And then the next one is, this has an index, a sub an index vector, and that equals another PD array. So it does some checks to make sure that your scatter index vector is the same length as your as the array you're trying to scatter, right? So it does that, and it'll throw an exception if they're not the same. And so that's sort of index manipulation. And like I said before, that comes through this other file through the PD array class 478. Line 478 currently is where the set item is. So self, key, and then value, and then we pass different messages based on what the index vector looks like, or what the index value looks like, and what the and what we're setting it to. Let's see. There are other stuff in here. Any and all are reductions. So we support a whole bunch of reductions. Like is sorted as a reduction, all, any, all these things. Sum, prod, min, max, argmin, argmax. So there's a huge number of things we've implemented basically so that our users can basically do what they do in NumPy, only on a much larger scale.
So Mike,
Yep.
Why haven't you implemented multi-dimensional arrays?
We have another 2-hour conversation on that. I will give you the short answer. The short answer is there are two different ways to implement two clearly different ways to implement multi-dimensional arrays. One is simulate multi-dimensional arrays with a one-dimensional block structured array. And that's actually the most space efficient way to do it. And it's actually not, we already have most of the machinery to do that, but the performance wouldn't be that great, right? And then the other end of that is if we did a true Chapel two-dimensional block structured array or something, we would blow up the code by a factor of 2. Right. So the server code would automatically, because we work on once we get into Chapel, we're locked into statically typed situations. So then we have to call specific code. And so you're stuck in this place where the number of operators times the number of types, right? So you're like, you have to implement, like if it's a 2-operand thing, and I implement 15 operators for integers, right? And I have to do int, float, int, right? So I've got to do all the type combinations for every time I have plus or something, right? So it gets to be, we've had a couple of design conversations about how to do it. One thing we've thought about doing, and we since we need a consistent model to pass things through the symbol table, like from one operation to the next, we have to be able to, if we kept, I'm not going to go down the rabbit hole, but it goes pretty deep, right? I mean, it goes deep enough that we have had it on the books as a requirement for almost 1.5 years or 2 years almost. And we have not done it because all of our use cases have been that people have really pushed for have been one-dimensional use cases, like data framing, column store kinds of things. I think we're going to end up doing the slower of the two implementations. And then if we need to get speed, we're going to do a transpose from a 1D to a 2D and then do the operation, right?
Okay.
Because one of the things that we have to do is have a place in the symbol table where we can have some sort of consistent mapping, and we don't want to like soak up all the memory that we have by having extra blank memory because this thing was a two-dimensional block array or something, right? Excuse me. Does that make sense at all to you?
Well, I certainly understand it adding levels of complexity. I guess you know, and you obviously don't have a use case that's driving it, or you would have bitten into it. Yeah. I do kind of wonder if it's one of these things that if you had the feature, you might get people might find other use cases or something like that. So,
well, I know that's the case, right? I know it's the case, right? So I don't want to throw mud like on anybody, but when we first started this project, the compile times for Chapel programs were pretty long. Mm-hmm. And it still takes 200 seconds on my Mac to compile the server, right? So when I get into a debug loop or something, there was a point where it took 700 seconds to compile. And that was, that's more than 10 minutes, right? So your debug loop is like, wow, do I remember what I was doing 10 minutes ago?
Oh, we're so soft these days.
I know it is, but
no, that's all perfectly valid. So
we have users that have wrapped. It is possible to make a two-dimensional PD array wrapper in Python. Mm-hmm. And we have users that have done that for themselves, but we haven't chosen to share their code with you guys, right? Part of it is whenever we do something, there's security concerns about sharing it until it gets reviewed, and then we end up months later, right? And it is a valid point. I've had people also ask for, in particular, for all the operators to be expanded by one by allowing us to do complex types, right? So like for add, we went from integer, float, and Boolean, right? And so it's basically n choose 2. So that's 3 choose 2, right? Mm-hmm. Different combinations. And then if we added the complex, it would be 4 choose 2, right? Different combinations. So it's almost a square, right? Like it's a squaring problem when you add another type to the server, right? So which is one reason why we haven't added anything beyond 64-bit and 64-bit float and Boolean, right? Sure, go ahead.
Can I ask a question?
Sure.
So how much of a concern is this sort of extensibility to you? So for your example, when you said somebody came and asked for complex, how often do you think that's going to happen?
It's never happened. Complex is the only basic, what I would call a element-wise data type that's been asked for beyond Boolean, integer, and float. We also implement strings, but we don't implement all the operators, obviously, for strings.
Okay.
Strings is a more complex. Strings is a segmented array approach. We had somebody come in and say, I want to deal with every domain name on the internet in an array.
Okay.
Right. So that was like 50 billion strings or something like that.
Okay. So these are basic types. Looking forward to, let's say, algorithms.
Yep.
Do you, or is it the domain of such of nature that, for example, so like okay, my frame of reference here is kind of like graph BLAS, okay?
Yeah, sure.
Where you have operators on arrays, okay? And then you can redefine them operators every single time you implement a new algorithm, yes? This is kind of how it works.
Yeah.
Right.
You have a semi-ring and you do your thing, right?
Yeah.
I mean,
Right,
it's yeah.
Do you expect people that use this system kind of code in the same spirit?
Yeah, so we've had people, I mean, we're looking at implementing like graph BLAS type operators. We implement internally. So in the repo, there is there's another directory called akutil, and people have gone off and implemented their own stuff, and we've included some of it there as sort of more examples of how to use it. And one of the things that we were concentrating on originally was one-dimensional arrays and segmented sparse things, like how we implemented strings. Strings is one big data array, and then there's an array of pointers to all of the separate strings. And we also have we have an implementation we use every day internally for sparse matrices, which is basically just compressed sparse row or compressed sparse column. It's really because we just needed the functionality. It needs to be fast enough for a person to sit at the command line, type something, get an answer. Graph BLAS is like, I would love to be able to use like one of the C libraries that implements graph BLAS or something like that, like under the covers. It shouldn't be terribly hard, but there's design questions on what kind of object are you going to store in the symbol table? And we're currently having a lot of discussions internally about how to extend the symbol table so it stores more than just one-dimensional arrays.
Okay.
Because currently complex objects are all stored in Python. So like strings is 2 PD arrays. It's one as a set of pointers of int64 and one as a set of data, which is uint8, right? And that stores a UTF-8 set of strings, right? Yeah. And but we've also so we're talking about maybe implementing a segmented array class for Chapel, and also implementing some other things, tools that would allow us to sort of spread out the different things that we can offer out of the symbol table. Okay. It is, like I said, there's I just got 2 more people to work on our team, so I've got 5 people now. It's not just 2 anymore, so we're spreading out and we're implementing some more things. But I'd love to, if you want to have a design conversation about like what you would want to implement, I think that a lot of things, there's a lot of things. We implement all kinds of things that are represented by one-dimensional arrays. And then we have like an adapter that can take that one-dimensional array and turn it into whatever we need it to do. So we can do the algorithm on it and then turn the result back into a one-dimensional array.
Yeah.
Right. So that's sort of how we operate today, because the symbol table is really that object store where all the communication between operators happens, right?
Yeah. All right. Yeah, I mean, so we have a lot of design ideas, but we also need to understand your programming or intention constraints. Okay.
Yeah, it is.
It looks to me that you guys have a preferred way of developing. Yes.
Well, it is. It is that way mostly because, we've had such a small team and we've had about 20 users internally sort of giving us requirements every week, right? So it's sort of like, what's next on the list and how are we going to get it done, right? We had a mathematician implement his own server operations. We've had that happen. He implemented a HDB scan graph algorithm and some other things in Chapel. So we've had both ends of the spectrum. One of the things that we've wrestled with a lot is, and I don't have a good solution for this, is how to include optional content. So we've talked about doing FFTs, like linking FFTW into Arkouda, and then how would we do that? And there's a Chapel wrapper for doing FFTs with FFTW, and can we do that? How does that map to, we needed 2-dimensional FFTs, or basically big 1-dimensional FFTs. But once you do that, currently the server is statically compiled together, and you're sort of stuck. Like if you're building it, you have to take the source and sort of link in the thing you want and create a couple of things in the source code to hook your stuff in. And there's no sort of dynamic way of linking stuff into Chapel. One of the ideas that we have has there's an idea that we have, which basically, let me go back to the where is, because I think you might find this interesting. I don't know how to make it happen, but it is it's something that we want to do, right?
So is Chapel still source to source compiled?
It is source to source, but we're still on the verge of having the LLVM backend as the default.
Okay, because I mean, if it's source to source, you can dynamically link in the C sources.
Yeah, there's just not a good flow for a regular regular developer to do that.
Yeah. But I mean, with assistance from them, they can modify the make files and
yeah. So we have talked about factoring. Do you know what Apache Arrow is?
Yep.
Okay, so we've talked about factoring the server into something that's Arrow-like, right? So the object store and the symbol table becomes a separate program, right? And the code modules and message processing becomes a separate set of programs that connect to that. And then the dispatcher becomes a separate program, right? So the other problem that we're experiencing, though, is that there's not a clean way of doing this linkage across programs from a Chapel program, right? So if these 3 pieces are in Chapel, how do we actuate that sort of dynamic registration and calling and getting access to memory and stuff like that, right?
Yeah.
But it is something we've thought pretty deeply about. The Chapel ecosystem isn't up to it yet. That would be an awesome thing if we could get there, because it would significantly simplify how the server gets put together, and that would actually make the inclusion of new modules and things, it would make it a lot more approachable.
Yeah, so we should talk with it, because Zoran and I discussed exactly this angle. Okay?
Yep.
How we get more jitting and whatever dynamic behavior in and out of these things. So we should. It looks like you guys are facing exactly this problem. It
is exactly this problem.
So, okay, so we should follow through.
Okay. Does have I covered enough of the sort of structure of how the code goes together? I did want to show. Does anybody have any questions at this point? Any other questions? Unless I bored people to tears. It's kind of hard to walk through code and stay awake for a long time. So we are, let's see, we're approaching 3:25. So at least that's what my clock says. Okay, so we've been on for almost an hour and a half. Let me go back. So one of the most interesting pieces of Chapel code that we have in the server. So you've seen the very, very high level code, which is like A plus B, right? I mean, that's the reason why we chose Chapel in the first place, so that we could basically have the server, basically almost a one-line statement in Python would map to this one-line thing in Chapel, right? and we can still get fair performance, element-wise performance out of it. And we've seen that. We've done performance analysis, and Elliot has some slides that he showed at one of the meetings I was at where, you know, we're on par with NumPy on a single node, and we can also scale up to multiple nodes, and the performance for most operations scales linearly with the number of nodes and the number of cores. Let me go here, and there's a file in here that's sort of like the jewel of the whole server, which I wrote in a fit of rage one day. It's called radix sort LSD. LSD stands for least significant digit. It does not stand for the drug. Although I think by the time I was done with this code, I thought I'd been drugged. And this is an array level routine. This is a package for, we needed a sort that was basically agnostic to the structure of the data, because we needed some, and there were no parallel programs out there or parallel libraries where we could just link in an NPI library that was a general sort. Most people specialize their sorts on HPCs, and we needed to have something that could take anything the user threw at it, basically. So this file, radix sort LSD, this is actually one of the most performance critical pieces of Arkouda that we've worked the most on with respect to performance. This is the reason why the COM aggregation module was invented by Elliot. And so down here on line 146, we have this radix sort LSD underscore ranks. So there's two different sorts. One is a keys sort that just sorts all the keys. Ranks actually sorts a tuple of a key and the original index so that you can spit out a permutation. So that we can permute the other columns in a data frame, all the group by stuff that we do, multi-level sorting. We can sort, we can aggregate multiple arrays into a key, and it will take, you know, a sub I, you know, it'll take the ith element from each array and aggregate it into one key, basically. And it calls this radix sort LSD ranks under the covers. So we check for it sorted. This is a piece of Chapel code that sort of represents the like complete control. This is like using both MPI and OpenMP in the same thing, only it's all Chapel code, right? So the first thing we do starts on 174. We have a, we count the digits. You know, it's basically just a counting sort. And then we, in the middle on 205, we basically do a scan across all the counts to basically find all the bucket breakpoints. And then we calc all the new positions and we permute it all, right? And you'll notice that there's an outer loop across locales, right? And then there's an inner loop across tasks on each locale. Right. So that's sort of like the the MPI level and the OpenMP level, or the process level, you know, the locale level and the sort of on locale. But I was really surprised at how short the code ended up being. I mean, the ranks code only goes from 146 to it's not even 100 lines of code, right? 259. So it's like 100 lines of code effectively to do the sort. Now we use these aggregators, copy aggregators, source aggregators, and destination aggregators. You'll see that they're in the code here. That allows us to write code that looks like single word traffic, but all the communications are aggregated into buffer moves. And the buffers are basically index data. So it's basically vectors of scatter vectors, basically. Anyway, and we just recently I guess there's a new version of Chapel that basically has some enhancements. It uses some enhancements because it runs on GasNet on the IB systems that we have. And so there's some enhancements to GasNet, and I guess that's coming out next week, right? In the Chapel release, Brad?
Yeah, that's right. That'll be out this coming Thursday, the 15th, I think it is.
Yeah. So we use these aggregators all over the place. There's a bunch of tunables in the code. You could say use more cores, use less cores. We're currently running a whole lot of stuff on dual roam socket nodes. They basically have 64 cores per node and 2 terabytes per node. We're running on a lot of nodes that look like that now, and everything's working pretty well. One of those is about 4 times as powerful for our code as the Cray XC nodes that we ran on before. So it's 128 cores versus 32 cores, and it's a 200 gig IB versus 40 gig Aries connection. So you would expect it to be about 4x, and I think we're hitting about 4x right now on a per node basis. That means that running 16 nodes on the new system looks like running 64 nodes on the old system, on the older XC40s that we have. Okay. Is there any more questions about the code or like design choices or anything you want to see that you've seen in the code you want to look at closer? Or
Hi, Mike. This is Jeff. This last example really kind of got me thinking. I think Costin asked the question yesterday about kind of how you would batch operations together on the client side so they could be optimized when they were shipped over to the server. And based on what this looks like, you can extend the Arkouda server relatively easily. So
pretty much any way you want.
Yeah.
Right?
So there's not, if it's something you're doing a lot, you just decide to go, and you can go and write the routines yourself on the server side, and that's exactly where the optimization comes from.
That's exactly what you do. Let me show you a quick example. Let me show you a quick example, because this is an example of something that we actually did. So there's a PD array set ops.py, and let's look at let's see, what are we looking for? That's unique in 1D, concatenate. Here's union 1D. Okay, down here on line 263, it takes 2 arrays. It's an operation. It takes 2 arrays and takes the elements from each array and unions. It gives you an array as a return that's the union of those 2 element sets. Mm-hmm. Right? And so when you go down into this code, let's see, we originally wrote this code. We just ripped some code directly out of the NumPy repo, and we implemented the union, and that's this code down here on line 311. Mm-hmm. So we optimize the integer case. So on line 307, we optimize the integer case when PD array 1 and PD array 2 are both integer typed arrays. Right. We pass this union 1D message that goes to some specialized code in the server.
Okay.
Right. but down on 311, if the types of both arrays are not integer, like let's say they're strings or something, because we support union on string arrays, string arrays. It does a cast of a PD array, and it does the unique of each array and then concatenates them together. Anyway, so it basically gives you, it basically concatenates the two arrays, then it dedupes all the elements and passes you back the thing, right?
Mm-hmm.
So this code on 311 used to be the code that was executed all the time. And we went in and said, we really want integer sets to be faster. And we ended up speeding it up by like a factor of 3 or something by creating just a union of two arrays, right? As a specific operation in the server, right? And you can still see, you can see that more interesting one is intersect 1D, which means you're intersecting 1D arrays. This is a function that's directly out of NumPy. We mimic the with the interface exactly, right? And this one says here on 363, you know, if we're integer types on both sides, we have a specialized message that goes over. And if we're not, then we have a flag that says you can assume everything in these arrays is unique, or you can not assume. And if you don't assume it, then you have to actually call unique on it, which basically dedupes everything in the array first. And then it merges the two arrays and then does some index magic to make sure that if two adjacent elements have the same value, then they are in the intersection, right? So that's what this logic down here on 370 down to 374 does, right? And it uses the NumPy way of saying it. And this is probably 11 server operations versus this one on 364, right? So yeah, so you have these different tiers of optimization you can do. You can either implement the whole thing as one server operation, or you can refactor it into maybe some more complex server ops. One of the things that we do, let me go back here. We have a message called find segments.
So Mike,
yeah,
in terms of software engineering, you are mixing metaphors in that code, yeah?
Mixing metaphors. I mix metaphors all the time.
You send a generic message to something and then
yep,
you are using Python, so probably you can rewrite that to everything look like Python.
Yeah, you can. There's multiple levels of implementation that you can engage in, right? Yeah. I mean, that's really the message,
yeah,
right? Is that you can implement it using already existing server operations directly out of Python, or you can implement it completely in Chapel, and you can actually do stuff in between, right? You can refactor code however you want, right? So it's it's something that we've engaged in quite a bit. Typically, the very first implementation of something is usually all in Python, and then if we decide it needs to go faster, we re-implement it. Anyway, does that sort of answer the mail for you, Jeff? I mean, that was sort of the.
Yeah. That I just wanted to confirm that's what you were thinking.
Yep.
I mean, we were thinking about. I mean, we're heterogeneous computing advocates, and so I'm trying to think about how we would pull a thread from the client all the way through to make use of something that may be resident inside a GPU.
So
something like that, right?
So Adam. The only GPU support we currently have, right? Adam Thompson from NVIDIA basically grabbed our code, and he enabled a path for us to binary serialize from into the client. So if the client has a GPU and you have NumPy, right, you can basically take a PD array and binary serialize it into a number array, basically.
Okay.
So, but you could also, one of my hopes, right, is that we'll get to a place where we have GPU iterators in Chapel.
Mm-hmm.
The Chapel parallel iterator infrastructure should be rich enough to support GPU iteration. Even if it's not, it shouldn't be that. I don't think it should be that conceptually that hard to extend it. to be able to do that. So it's a it's a hope that we'll be able to, once we get GPU sort of parallel iterators in Chapel, we'll be able to spread PD arrays across GPUs.
Mm-hmm.
Right.
Sure.
But yeah, I mean, if you go back into the server, that server main dispatch loop basically has how many commands do we have? We've got, starts on 303 and goes to 375. So we have a bunch, right? I mean, these are all major, sort of like the major opcodes, right?
Yeah.
efunc is the elemental function. So like if you want to apply like the sign function to all of your elements in your array, that's what efunc does.
Okay.
Right. So that's on 333. And then efunc VV, efunc 3 basically does a 3 operand thing. And this is supposed to, this implements mostly the where clause, where in Python, in NumPy is basically like a mux for those engineers among us, right? It's like a 2-input mux. It says you get two inputs, A and B, and then you get a Boolean, and it says whether you're going to select A or whether you're going to select the element from B, basically into the output. Yeah, there's a whole bunch of reduction messages. There's also
Mike,
segmented reductions, for various things.
Yep.
So Mike, the process of adding custom messages is that fairly simple? You just use the generic message in Python, and then you extend the select in the server, and then
that's exactly right.
Python?
That's exactly right.
Chapel. Yeah. Okay.
So I brought up we have a page that needs to be updated, but there is a page in the Arkouda documentation down here called contributing. It's down near the bottom. And this sort of goes through a high level what you have to do to add new functionality to the server. So the first thing you do is add functionality into Python. We've listed out 7 things you need to do or need to be concerned with. Then there's an example of foo, right? A foo function in Python. And then there's adding functionality to the Arkouda server. And then there's a bunch of things that are listed here to do. Some of these things are outdated. We've changed some of the ways we do message parsing, and we've also changed a little bit about the exception handling and logging and stuff. But, basically you go into the main server loop, you say when foo call my thing, then you add your use your module in this thing called the message processing module. It's sort of a one place where we have all of the modules included. And then you create a foo message module. And so this sort of keeps you in the same style as all the other message processing that's going on. And then you sequester all your functionality basically into this foo message module. And you can have like, there's a foo function procedure in Chapel, and then there's a foo message which basically parses it and does a select based on what type you had, right? But these things can get arbitrarily complicated. We have some variable length operators implemented. One's called concatenate, which basically concatenates multiple arrays together. So let's say I have 4 integer arrays. I can pass a concatenate message that has 2, 3, or 4 integer, names from the symbol table, and it will go and concatenate those things as long as they're all the same type and size, or not size, but just the same type. So, but yeah, there's a basic sort of how-to. It's not great, but it needs to be updated, but it's the basic, the basic methodology for what you have to do. Once you do it once, it's not that hard.
Sure. So there are a lot of routines there. I guess, you know, there are a couple perspectives on that might be helpful. And that is, you know, just characterizing the workload. Is there, you know, a priority in terms of just frequency of use that segment those into, or
this is the reason why we trace everything, right, so that we can get all those counts. We trace everything. We trace the users. The users they know they're getting traced, right? You know, when they actuate the server. And then we had a data scientist on tap for 6 months that basically did analysis of everything. And we have some scripts that basically run against all the traces. And, you know, it's not hard to understand. Like, the thing that popped out, since people do group by the most, sort and coarg sort popped out the most, and IO is actually our biggest pain point, because IO subsystems,
we get that a lot.
IO subsystems, you know, if someone comes in and says, I want to read a month's worth of collect or something, and the next thing you know, they're waiting for 15 minutes. And, you know, then we had to really concentrate. Like, if it takes 15 or 20 minutes for somebody to load their data into an interactive session, they do not want that session to go down, right? They don't want the server to crash. They don't, you know, so we worked for months to basically try to make things as bulletproof as we knew how to make them. You know, whenever we get an exception in Chapel, we pass it back to Python, and Python throws an exception, right? So we had to implement that path. And anyway, so is there anything else?
Well, the second question along that line was just the frequency of use, but then a time-weighted frequency of use. So that, you know, if you looked at how much time is spent in each one of those functions and you add it all up and rank them.
So the most heavyweight operations, again, are the sort and the, you know, and the IO. Right. We sorted, I don't know, is Elliot on? Are you on, Elliot?
Yeah, I'm on.
You can, I mean, it's your thunder. You know, you sorted a 60 terabyte array. You can tell people about it.
Yeah, I think that's the current high watermark. I mean, you were mentioning the system with the dual socket Rome chips with 2 terabytes of memory on each. And on that system, we'd sorted, I think, a 60 terabyte array in under 5 minutes. And that's kind of currently the, you know, the high watermark for performance there.
Cool. Good.
So the longest an analyst has to wait is usually when they do a group by or some sort of sorting operation, right? Most things, let me go back real quick to this thing. I know it's in here somewhere. Oh, here it is. So we made some basic timings on 50 billion entry arrays, and these timings are about a year old. So some of it's a lot faster now, but like scalar reduction, histogram, vector ops, logical indexing, these are all in seconds. Reading, you know, 50 billion, you know, depends on your file system, right? But these are all in seconds, and gathers can be slow if you have a hotspot and you can't control that. Like you have a small lookup table and you have a huge vector and all these guys are going at the small lookup table, right? And so you got all these memory references sort of stacked up trying to get elements out. Sorting, you know, 50 billion elements is, you know, a few seconds, right? And grouping is maybe double that, because you have to sort and then you have to sort of segment everything and know where all the group boundaries are. And then aggregation is a similar kind of thing. So, you know, sorting is sort of our benchmark for like how long the longest things take, right? So
very good, thank you.
So that's sort of, and these were ordered by Bill Rusin to, you know, like you want to summarize or you want to filter or you want to enrich or you want to do something else. And he sort of chose representative operations from each one of those categories.
So yesterday, Kostas asked whether there was opportunity for optimization. And today I can see that you actually have a number of ways that you have optimized operations. And yesterday you said that optimization was not your pain point. So can you tell us about what is the pain point? What are the pain points? I heard I/O.
Yeah, I/O is definitely a pain point. Our new system, can I even say, we have some of these flash arrays that, have like a petabyte of flash and have, 8 InfiniBand ports on them. Things like, we have some I/O subsystems that are actually pretty beefy. We're pretty excited about the usage of like fabric attached memory in this realm. To like save and restore, fast checkpointing on objects that we need to be able to restore, especially if like a server crashes or something, we might want to checkpoint to something. Let's see, in operation land, we're running up against a place where we do need to do something against the more complex objects, like 2-dimensional matrices and multi-column operations on a data frame, because we're constantly traversing back and forth between the client and the server. Sorting strings is still, we're a lot better than we were, but it's still 5 to 10x slower than sorting integers. There's also some integer sorting. There's probably a 5 to 10x uplift on integer sorting that we could get, but we haven't had to sort of pull that trigger yet. It's going to be interesting when we put our new system, when we like give the users access to the new system, because it's got twice the memory per performance per node, right? So we went up by a factor of 4 in performance, but we went up by a factor of 8 in the amount of memory per node. So it's going to be interesting to see what they do. One thing that they do like is that most things are fairly predictable in how they perform, so they know whether they need to go get a cup of coffee or not, right? Anyway, did that answer your question? I maybe I went off into the weeds, but.
Well, it was an open-ended question, and yeah, that was good. Also, yesterday when you loaded from the CS, okay, so here you can read from the disk efficiently if the data is already in HDF5.
Yes.
Okay, but in yesterday's example, you started with a CSV file, which you just read in. Is there a very efficient way to do that in parallel? Or
CSV in parallel is a really hard problem. And the reason why is because sometimes like the Pandas CSV reader actually makes multiple passes over the file. It reads a column at a time and it does some craziness and it tries not to use too much memory, but then sometimes it uses a lot. So reading CSV, if you ever want to hear like how hard it is to do CSV in parallel, ask the guys at NVIDIA, because they've implemented some CSV readers for the GPU. And it's really not conducive because you have variable length strings and you have all these variable length fields, and it's very difficult.
Is that painful?
Yeah, it's very painful. It's very, because there's a lot of edge cases, and it's very hard to get code that's bug free or as close to bug free as you want, because of all these edge cases you have to deal with.
How important of a problem is that for you to solve?
What we do currently is we get a stream. All of our data comes in a stream of files. So you can think of it as it's a stream of data that was separated into a bunch of medium-sized files, a couple gigabytes. So what we do is we currently launch a Python or Java process to basically translate that CSV on a per file basis into HDF5. And then once we get into like read HDF, can accept a glob expression. So you can say star.hdf in a particular directory. It will suck up all the files and it will concatenate them into a big array. All the fields that match will get concatenated into big arrays.
All right, so it looks like you have a intermediate, because for example, now that you described the CSV is a problem, CSV reading is a problem, I think we know how to solve it, okay?
Yeah, sure.
But looks like there are workarounds maybe.
Yeah, I mean, that's how we work around it currently. We have to do ETL, you know, extract, transform, load on all the CSV, and it's very often some minutia that you really don't want in your main processing flow. You really have to do it sort of pre-analyzing, right? Because it takes a data scientist usually a day or two just to figure out how to read the data, right? Because depending on if it's a new schema or something, right? I mean, we have 3,000 different data flows we have to parse, right? I mean, it's crazy, right? So they all have to be normalized and parsed, and it's 3 people's full-time job, you know, on our team. Anyway, IO is a really hairy subject, and it's something we decided, you know, early on. You know, Python had support for HDF5. Chapel had support for HDF5. We're going to standardize on something that was easy, basically, right? And since it's a columnar format in the file, that really matched up to what we were doing with data frames. So that's how we did it.
Okay, thank you.
Any other questions? Was this detailed enough, or did you want some more detail on something else? If you need anything more or more detail, I could have you know, we could do some more specific thing, or you could drop a issue in the repo. And that's sort of, I look at all the ones that come in, and we've had feature requests, we've had questions, we've had all kinds of things. We will, if you do get to the point where you implement something and you feel like maybe you want to help us out a little bit with the documentation on how to add something to the server, you know, feel free to edit the doc and, you know, submit a pull request, and we'll take a look at it. I've accepted pull requests now from 18 or 19 different people. So it's not, you know, I'm pretty easy about that as long as it doesn't break the flow for me. And we have 200 and some odd unit tests now, 220-ish unit tests that run in the CI flow. So as soon as we, you know, you can see whether you broke anything, basically. It's the same thing that if you run make test, like if you pull the server down and run make test, you'll run all 220 tests or whatever. So let's see. Elliot, is this particular thing? Can you guys see the screen? This Arkouda sort performance on the XC, is that still about right?
It should be pretty close. I think we're probably at like 140 or something.
Okay, so it's gone up by, you know, 15% or 20% or something. 15%.
Right. So there's been some non-trivial improvements on XC still, but you know, recently a lot of the improvements have been on InfiniBand.
Yeah. Yeah. I mean, this is argsort on FDR InfiniBand, but actually the InfiniBand is really a lot better now. Right. So, and this slide is actually going back to that intersection. This slide is really, this was the original code that we had in Arkouda for intersect, right? But then we went in and we made some things. We added stuff last summer, like we have min and max K, which basically says without sorting, do a heap reduction of an array and tell us the top k values out of that array or something. You know, we need that for a lot of times for you know, filtering off things that are above a threshold or something like that, right? So there's all kinds of stuff in there. Like I said earlier, the API reference goes through all of this, is generated automatically with Auto API, and it goes through all of the different packages in Arkouda, and then the chapel reference. These are all of the chapel modules, right, that are in the server. We've had requests for like Parquet format in the IO space, and we've also had requests for something called ZAR IO, which I don't really know a whole lot about, but we've sort of put those off because, you know, we got 5 people. It took a person the better part of a month, maybe a month and a half, to get all the IO into a shape where, you know, for HDF5, right, into a shape where we could use it. So, all right, well, it's 4, and if nobody has any other questions, I'm sure you all want to get away from me. So it was a pleasure to do this walkthrough for you guys. If you got any questions, don't hesitate to drop, especially if you have a question you want to ask the team, you can drop an issue in the repo, and I'll take a look at it and tag people on it who I think might have an opinion. So, all right.
Thank you.
Sounds good.
Thanks, Mike.
Yep.
All right. Thanks, Mike.
Have a good weekend. Thank you.
Share. Okay. Thank you guys. Bye.